Let us learn about a very interesting phenomenon of buoyancy today. Buoyancy plays a very significant role in the stability of floating and submerged bodies. So let us define buoyancy first. We know an object submerged or floating in a fluid experiences an upward force. Ship, which is a floating body, and submarine, which is a submerged body, both these bodies experiences some upward force, and this upward force exerted by a fluid onto the floating or submerged bodies, it is known as buoyancy force or force of buoyancy. In this lecture we will address an issue of determining magnitude of this buoyancy force, and where does this buoyancy force acts we will determine. In addition to this, we will focus on a very important part of conditions of stability. Floating bodies like ship and submerged bodies like submarines, how they remain in a stable condition and what different conditions we have to achieve this stable equilibrium we will study in this lecture. So first we will determine magnitude of the buoyant force. So to do that, let us consider we are having an arbitrarily shaped body which is submerged in a large expanse of a liquid. So liquid is having a density of rho. This is the free surface of a liquid, and let us take a very small element from this body which is having a cross-sectional area of dA and a very small volume dV. So the top face of this element, it is at a depth of h1 from free surface, and its bottom face, it is at a depth of h2 from free surface. So let us assume the atmospheric pressure is P0. So we are considering here this atmospheric pressure equals to 0 because we are talking about gauge pressures which are nothing but pressures above atmosphere. So now we have identified pressure variation in a fluid. We know in the horizontal direction there is no pressure variation. Pressure remains same in the horizontal direction. But in the vertical direction, as the depth go on increasing, pressure also increases. So if we consider this bottom face, the pressure acting here will be greater as compared to pressure acting here at the top face, because depth of this bottom face is higher. So at this location pressure will be higher as compared to this pressure, and hence pressure forces acting onto the bottom face is greater as compared to pressure force acting onto the top face. When we talk about these horizontal forces, as we know in the horizontal direction pressure is same throughout. So what will happen? Pressure forces in the horizontal direction, they will cancel out each other, because of which there is no net force in the horizontal direction. But in the vertical direction there will be a net upward force acting. So it's a net upward force because pressure forces are greater at the bottom face as compared to pressure forces at the top face. Now we will determine what is the magnitude of this net vertical pressure force acting onto this element. We know P is equal to rho gh. So it's a hydrostatic law that pressure is equal to rho into g into h. From this pressure we can determine pressure force. So let us determine now net vertical pressure force on the element. So now this bottom surface or bottom face if we consider, so let us say at the bottom face pressure acting is dF bottom, small force. At the top face let us say pressure force acting is dF top. So what will be the net force acting in the z direction? So it will be dFz, which is nothing but dF bottom minus dF top. So dF bottom minus dF top, it will give you the net vertical pressure force. How to determine its magnitude? dF bottom. So force is pressure into area. At the bottom face pressure is rho g h2 multiplied by area is dA, minus at the top pressure is rho g h1 multiplied by area dA. It will give you pressure force at the top. So solving this, what we will get? Taking rho g and dA common. So rho g into h2 minus h1 into dA we will get. This h2 minus h1 is nothing but what? h2 minus h1. It will give you height of this element. So height multiplied by its cross sectional area, it will give you dV, which is the volume of the element. So it will be equal to rho g dV. Now this is the force which is acting onto this element only. If we consider all such elements throughout this body, and if we sum up all these elements, we will get the total buoyant force acting onto this. So summation means what? We are taking a volume integral because here we are considering a volume element. That's why a volume integral of this rho g dV we are taking. So rho g is constant, so taking it outside, and integral of dV will be equal to V. So buoyant force is nothing but equal to rho g into V. So we know rho is mass per unit volume. So this is mass per unit volume of the liquid we are considering multiplied by G into V. So this V is nothing but what? It's a volume of the element. So in case of a submerged body, this volume of the body, it is equal to volume of fluid displaced. So mass per unit volume of fluid and this volume can be considered same. So this volume will get cancelled out, and what we will get? Fz equals to mg, which is nothing but equal to weight. So this W is the weight of the fluid displaced. It is because volume of the element and volume of the fluid displaced, they are one and the same, because of which we can say now buoyancy force of the fluid, it is equal to weight of the fluid displaced, and this is known as Archimedes principle. So Archimedes principle states that buoyancy force of the fluid, it is equal to weight of the fluid displaced. Now if we consider floating body, in which what will have some part underwater and some part will be outside. So whatever the part which will be inside the water, it's nothing but only the volume V. So this volume V, it is nothing but what? The part which is immersed, and this is the displaced volume. So weight of the displaced volume, when we are calculating, only this volume we will consider. So buoyant force in this case will be equal to what? Weight of the fluid which is displaced. In floating bodies, it will be the part of the body which is under water or under fluid. So this is all about the magnitude of buoyant force. Now we'll have some comments onto it. So let us consider a body which is in a state of equilibrium, submerged body. So this is a fluid and this is a submerged body in a state of equilibrium. It means that this buoyant force and weight of the solid body, they should have same magnitude. If they have same magnitude, then only they can remain in equilibrium. The second thing is the line of action of this buoyant force and weight of the solid body should be same. If the weight of the solid body, if it is acting somewhat here, what will happen? The line of action, as they are different, they will form a moment, they will form a couple, and this body will get rotated. It will not now remain in a state of equilibrium. And this point, it is known as the center of buoyancy, which is defined by C or B. Center of buoyancy is nothing but centroid of the displaced volume. In submerged case, volume of the body is nothing but equal to the volume displaced. So centroid of the displaced volume, it is nothing but the point through which this buoyant force acts, which is known as center of buoyancy. Now the comments are, we have determined that buoyant force is equal to weight of the fluid displaced. Second is buoyant force acts through the centroid of the displaced volume, which is known as center of buoyancy. And next is, for floating and submerged bodies to be in a state of equilibrium, the weight of the body and buoyant force should be equal. And in addition to this, weight and buoyant force must have the same line of action to have a zero moment. Then only they will be in a state of equilibrium. So now after this, we will discuss about stability of the submerged bodies. How the submerged bodies remain in a stable condition, we will see. So let us consider, we are having a submerged body of this shape. So this body is immersed inside the liquid, and this is nothing but a body axis, or it is also called as the axis of symmetry. Now we will determine from where the buoyant force acts and from where the weight of the body will act. So we identified that center of buoyancy is nothing but what? It's a centroid of the displaced volume. If this body, if we take out, it is nothing but what? This is the volume of the fluid displaced. So centroid of this volume, if we consider, it will be nothing but equal to what? The center of buoyancy B. Now if we consider the mass of this body is uniformly distributed, what will happen? The centroid of this body will be nothing but equal to its center of gravity. But now if the weight is not uniformly distributed, mass is not uniformly distributed, the center of gravity may shift along this axis. Now let us consider a weight we have kept on the bottom side, and because of this, as more mass is on the bottom side, the center of gravity will get shifted onto the bottom side. So here we will have center of gravity, and at the centroid of this body we will have center of buoyancy. Now at center of gravity, weight will act in the downward direction, and at center of buoyancy, buoyant force will act in the vertically upward direction. And this body, it is now in a state of equilibrium because this W and FB are same, its magnitude is same, and they are acting along the same line of action. Let us consider now some disturbance is caused onto this. Some force is exerted, so external force is exerted, because of which this body has got shifted like this. And now there is some angular displacement because of external disturbance. So axis now will get tilted like this, and this center of buoyancy and center of gravity, they will now move, they will remain as it is with respect to the axis, and because of which now if we plot the center of buoyancy and center of gravity, they will remain as it is along this axis, and their relative positions will also be same. At center of gravity, weight will act in the downward direction, and at center of buoyancy, buoyant force will act in the vertical direction. But now the line of action of these two forces, it is not same, because of which they will form a moment, or they will form a couple. And because of this weight acting in the downward direction and force of buoyancy acting in the upward direction, they will form couple in this direction. So the couple will be in the anti-clockwise direction, and which will be a restoring couple. So this is the direction of a couple, and this is a restoring couple. It is known as restoring because the position of the body will be restored because of this couple, and the body will come back to its original position again like this. So this type of equilibrium, it is known as stable equilibrium. So in a stable equilibrium, even though the external disturbance is caused, the body will come back to its original position. And what is the condition required for this? The condition is B is above G. The center of buoyancy, it should be above center of gravity. Then only the body will be in a stable equilibrium. Now consider the second case, in which what we have is, we are placing a weight onto the top side, because of which the center of gravity will now get shifted onto the top side. So here the center of buoyancy will have, and here the center of gravity will have, which is above B now. At G, the weight will act in the downward direction, and at B, the buoyant force will act in the upward direction. Let us consider some external disturbance is caused onto it, and because of which some angular displacement this body has undergone. So body axis will remain as it is, and the relative positions of B and G with respect to the body axis will be same. So now the G and B will be here. At G, weight will act in the vertical downward direction. At B, the buoyant force will act in the vertical upward direction. Again, the line of actions are not same, because of which they will form a moment. And now because of this action, buoyant force upward and weight downward in this position, it will form a couple in this direction, and this couple, it will result in overturning of this body, because of which it is known as overturning couple. So when G is above B, what is happening? The couple formed by buoyant force and weight, it is giving a overturning action, whereas in this case, when B is above G, the restoring couple action was given. And now what will happen? Because of this overturning couple, the body will get overturned. It will not come back to its original position, and hence this equilibrium, it is known as unstable equilibrium. So in unstable equilibrium, the body will not come back to its original position after having some external disturbance, and this condition will be there when B is below G. So now we can define conditions of stability of submerged bodies, like when B is above G, the body will be under stable equilibrium, and when B is below G, the body will be under unstable equilibrium. Now let us consider now a third case, in which we are placing a weight at the center. So weight is placed at the center so that the mass is uniformly distributed throughout it. So what will happen now? B and G will now coincide with each other, and because of which now the buoyant force and weight will act through the same point. So they are acting through the same point as well as having the same line of action. Now let us consider some external disturbance is caused onto it, and now the body will get some angular disturbance or angular movement, and now this B and G will have same relative positions with respect to the body axis like this. So B and G coinciding here, and now what will happen? The weight will act through the same point in the downward direction, and buoyant force will act in the through the same point in the vertically upward direction. Because of which what will happen? There will not be any movement, no couple we have, no moment we have. So body will remain as it is in the tilted position. So when this B and G coincides, no couple will get formed, and we will have a neutral equilibrium. So in neutral equilibrium, the body, after experiencing some external disturbance, moves to some new position and remain at that position itself, which is known as neutral equilibrium, and this condition will be achieved when B and G coincides. So now we have discussed about stable, unstable and neutral equilibrium with the help of relative positions of B and G. So this is all about buoyancy and stability of the submerged bodies. Thank you very much.